I'm Blue Origin, and I'm here to talk about aerospace. And obviously, centers are a huge part of the aerospace industry. There we go. That looks familiar. So, thank you for having me. And I see a lot of young engineers in here, and I want to tell you a story to kind of give you some perspective. It's something to think about as you go through your careers here. But anyway, I'm excited to be part of this conversation. Thank you, Bruce and Ravinder, for having me. Okay, so next slide, please. Nope. Nope. We have to go back to the beginning, please. There we go. Let's try that. Okay. Here we go. This looks familiar. All right. I always like to begin this talk by reassuring everyone that airline travel is by far the safest mode of transportation. That being said, there is a challenge that we have been wrestling with for over 100 years. And at the center of that challenge is a sensor. Originally designed to save lives, it's also caused a lot of heartache and despair. Okay. So do we have any pilots in the room today? Great, you're going to help me. Bruce, you're a pilot? All right, you all are, I'm roping you in. Okay, so for everybody else, I'm going to level set with some basic physics on how airplanes fly. So as airplanes fly through the air flowing up over the wing generates a lift force. And hopefully that force is enough to support the weight of the airplane. And airplanes, our pilots can control the altitude of which the airplanes fly by pushing a control in the cockpit called a yoke. So if they push the yoke forward, it noses the airplane down and they lose altitude, okay? Conversely, if they get too close to the ground and they want to gain altitude, they pull on the yoke, which raises the nose of the airplane, and they increase their altitude. They gain altitude, right? So pilots spend lots of time perfecting this movement, perfecting this set of commands to the yoke to adjust and fine-tune their altitude. And they do this thousands and thousands and thousands of times, right? And part of why this works is that the lift force is generated by the angle at which the air hits the wing. And we call this the angle of attack. And it's a linear relationship. The more you increase the angle of attack, the more lift you generate. Increase angle of attack more, you create more lift. But like a lot of things in life, too much of a good thing can happen, right? So my pilots, what happens if you keep picking that nose up and it gets higher and higher and higher? What eventually happens? Stall, that's right. So a stall is that once this angle of attack, there's a critical ceiling. And if that angle of attack exceeds that critical point, the wing just gives up, just suddenly stops making lift. I'm not doing this anymore. And there's no lift. Gravity takes over and you start falling like a rock. And this is called stall. Okay? Obviously very dangerous. Pilots want to stay away from this. They want to do everything they can to keep from stalling the airplane. And so that they have to do, the burden of the pilots is to make sure their angle of attack stays below this critical point. The challenge though is that this is the angle of air. Air is invisible. Pilots have this burden where they have to keep this angle of attack below this very critical point, but they can't see it. Okay? All right, pilots, hang back a minute. Let's test everybody else, see if you're paying attention. Okay, so the pilot looks up, and all of a sudden they're losing altitude. When they lose altitude, they want to gain altitude. What do they typically want to do? Raise the nose. They want to pull on the yoke, right? Problem is that in this case, and when they're installed, if they pull on the yoke, raise the nose, they increase the angle of attack, makes the stall problem worse. So these are the first two reasons of why stalls are so dangerous. First, they sneak up on you, you can't see it. And second, if a pilot does what they normally want to do, they make the problem worse. All right, pilots, join me again. What does a pilot do to get out of a stall? Push the nose down, right. Okay, so to regain the lift on the wing, the pilots have to do the opposite of what they normally want to do and push the nose down. So here you are, you're falling like a rock, and now we're asking the pilots to point the nose of the airplane towards the ground. And psychologically, this can be challenging. This is the third reason why I call stalls very dangerous, because the pilots have to do the opposite of what they want to do. And for this reason, I call stalls an error trap. It's easy for pilots to fall into, hard for them to get out. Okay, this sounds like a bad problem. How long have we known about this little bug or feature of airplanes? Over 100 years. Thank you. All right. We got a player here. Okay, so we all know about the Wright brothers. Before the Wright brothers, in the 1800s, we had lots of people doing important work in aviation and aerodynamics and inventing and discovering. One of the most famous is Otto Lilienthal in Germany. And Otto was experimenting and building wings and airfoils and building these human-sized kites and jumping off of towers and hills. So Otto is very famous for some important work in the early days of aerodynamics. There's something else that makes Otto famous. As far as we know, the first person to die from a stall. 1896, Otto was on his glider jumping off one of his towers, got this invisible angle too high, his wing stalled, fell like a rock, broke his neck. Speaking of the Wright brothers, 1903, they provided the first time demonstrated powered flight. So now we can fly indefinitely. Historic event, a huge leap forward in airplanes. After this historic event, the Wright brothers opened the Wright Airplane Company, started building airplanes and selling them. One of their customers was the U.S. military. So we think about the Air Force today, how big and strong and mighty it is. Well, it has some humble beginnings. It started out when they bought 8 Wright Flyer C airplanes. Very humble start to the Air Force. And everything was great until they, started flying them. And then they realized that, hey, if they pitch these up too much, there's this invisible angle, the wings will stall, and they'll crash. And they crashed 6 of their first 8 airplanes. Army said, wait a minute, these things are way too dangerous, and grounded the last 2. So kind of a rough start to the U.S. Air Force, but they seem to recover. But so this is a problem that Orville recognized. It's like, hey, I've got this cool product, but it keeps killing my customers, right? They have this invisible angle, and if they mess that up, they crash. And so Orville, being the inventor, is thinking about how to fix this. And Orville came up with a kind of a clever idea. He mounted a little wing underneath the main wing, and this little wing was free to pivot. And so therefore, it would kind of like a weather vane align itself with the angle of the air hitting the wing. And so a pilot could see the angle of this little wing and say, oh, okay, there's my angle of attack. Orville took it a step further, though. He actually hooked it up to an air tank and an actuator, and he could automatically move the stabilizer. So if this angle of attack got too high, this wing would float up, and it would automatically move the stabilizer and push the nose of the airplane down, preventing a stall. So this was very important development in airplanes, was covered by the media at the time. And they quoted Orville as saying that the problem of stability in air has been solved. He goes on to say that automatic stabilizer will make flying foolproof. You all know what foreshadowing is? Yeah, okay. Unfortunately, a year later, 1915, Orville got out of the airplane business. He sold his company. They stopped making airplanes. I don't really know what happened to this technology. It seems to have been lost, but anyway, that same year, 1914, airplanes started disrupting the travel agency, or travel industry. So the first airplane-based airline was in Florida, and it was an airboat that flew from St. Petersburg to Tampa. And it cost you $5, and it took you 23 minutes. So for context, if you're going to drive your car or ride your horse from St. Petersburg to Tampa, it would take you 20 hours. If you went by boat, 2 hours. This airplane, 23 minutes. Game-changing. And it kicked off a whole new industry of travel by airplane. And now people from around the world could travel to places that they've never been able to go to before because it was too expensive or took too long. What used to take hours now takes minutes with an airplane. What used to take days now takes hours. What used to take months now takes days. So this industry exploded. The challenge, though, is they all use airplanes, and airplanes share this common problem that if the pilot flying the airplane, now with a back full of people, gets this invisible angle of attack wrong, gets it too high, it'll stall and crash. In the 1940s, stall is the leading cause of aviation fatalities. And if we could just figure out a way to tell the pilots where they are on this angle of attack, we could save half the lives killed every year in airplane accidents. So, 1940s, Leonard Green was a young engineer at Grumman Airplane Company. His good friend was killed in an airplane accident when it stalled. And Leonard okay, we have to figure this out. We just need to let pilots know where this angle of attack is. So he invented and then patented the first stall warning system. And a part of that is the angle of attack sensor, the star of our show today. Okay? Here's a picture of it. We still use them today. How this works is there's a little metal tab that sticks out of the front of the wing, and when the air gets too high, it pushes that tab up, closes an electrical connection that can then send a signal to the pilot, warning them. Again, for context, if we can just warn the pilots where their invisible angle of attack is, we could save half the lives killed every year. This too got a lot of coverage in the media. Saturday Evening Post says it may be the greatest lifesaver since the invention of the parachute. Okay, so how this works is you have the angle of attack sensor on the leading edge of the wing, and when it senses that your angle of attack is too high, it sends a signal to the pilot. There you go. And what that looks like in the cockpit is that at first the pilots will see a flashing light and a horn saying, "Pilot, pilot, pilot, you're about to stall. Push the nose down, push the nose down." And that's how it showed up in 1940s. About 20 years later, we started escalating the notification by adding what's called a shaker. So the pilots are holding the column or the yoke, and we start shaking it. "Pilot, pilot, 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 hey, wake up, you're going to stall. Push the nose down, push the nose down." And then finally, we added a third escalation where we added a pneumatic ram that will physically shove the columns forward in the cockpit. Say, "Pilots, hey, you're stalling. Go this way. Push the column this way." Okay? So you look at this cockpit, we have lights, we have horns, we have shaking, we have pushing. We have made it so obvious to the pilot what's happening and what they should do. Right? So ladies and gentlemen, I present to you the stall warning systems that we still use today. So all the airlines that you fly today has some version of this. And because of this angle of attack sensor, we started the stall prevention strategy. So we're just going to keep pilots away from stall. And of course, airline pilots have their training and they're familiarized with these systems and know what to do when this stuff happens. Okay, so fast forward to the 2000s. How are we doing? Right now we've had the angle of attack sensor for 60, 70 years. Angle of attack is no longer invisible. We now have all the warnings and layers of warnings in the cockpit. So did we fix the stall problem? Well, I have some data here. This is across the globe air transport fatality data from airline accidents. For context, since the 1940s, the overall accident rate of airlines has plummeted. All right, by orders of magnitude, airline travel has gotten much, much, much safer. However, that number still is not zero. And this data set represents about 8,000 deaths across the globe during this time frame from 2005 to 2023. So, and it's categorized by the type of accident. So let's take a look. Does it surprise you to see that in the 2000s, stall is the leading cause of fatal airplane accidents? 60, 70 years of the angle of attack sensor, 60, 70 years of stall warnings telling the pilots that they're about to stall, and we're still killing people. What's going on? Let's drill into some of that data. February 2009, Colgan Air Flight 3407. It was flying from Newark, New Jersey to Buffalo, New York. It's a Bombardier Q400, state-of-the-art airplane with all the stall warning systems in it. During that flight, the pilots noticed that there was icing building up on the windscreen and the nose of the airplane, which can be dangerous. So the pilots were having a conversation in the cockpit about what to do with it, and as they're doing that, the nose of the airplane gradually drifts up. The angle of attack gets too high and almost stalls. The angle of attack sensor detects this as, uh-oh, we're stalling, set off all the warnings, set off the lights, the horns, the shaking. Pilot, 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 wake up, you're stalling, push the nose down, push the nose down. The pilot kind of looks up surprised, didn't really do anything. The nose kept drifting up. The airplane goes into a full stall, starts dropping. The final escalation kicks in. The ram activates and starts shoving the column forward. Pilot, you're stalling. Go this way. Push the column this way. So the lights are going off, the horn's going off, the shaking, there's pushing, all telling the pilot, push the nose down, push the nose down. Instead, the pilot looks up, sees his altitude falling, and does what he always does when he sees his altitude fall. He grabbed and he pulled. And he pulled and he pulled. He pulled 160 pounds against the system trying to save his life. 50 people died that day. There was nothing wrong with that airplane. Stall warning system did exactly as we designed it to do, but the pilot fell into that error trap anyway. Now you can say, well, that's human error. Pilots screw up sometimes, and yes, you could say that, chalk it up as human error. Many did. Just 4 months later, Air France flight 447, flying from Rio de Janeiro to Paris. It's an Airbus. As they're flying out over the ocean, they flew through a thunderstorm, and they too were collecting ice on the outside from the thunderstorm. And at this time, it was affecting their instrumentation. The instrumentation was freezing up, locking up. Not a big deal. All they have to do is turn on some heaters, and it'll melt the ice and fix the problem. But as the pilots were working on that, the nose of the airplane drifted up, and the angle of attack got too high, and the airplane stalled. Angle of attack sensor said, uh-oh, and set off all the alarms, the horns, the lights. Pilot, 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 you're stalling, push the nose down, push the nose down. Instead, the pilot looked up, saw his altitude falling, and did what he always did. Grabbed the stick, pulled, and held it for 4 minutes. Air Asia flight, there's another Airbus flying from Indonesia to Singapore. As they're flying over the ocean, the pilots noticed a computer problem. It was a minor error that showed up, but it was not a big deal. But as they were resetting the computers, trying to clear the messages, the nose drifted up. The airplane stalled, the angle of attack sensor set off the stall warnings. Pilots pushed the nose down, you're stalling. Instead, they saw their altitude, and they did what they always did. I could keep going on with these stories because NASA Langley did a deep dive into this stall data, and they found that 50% of the time, nearly 50% of the time, when we're presented with this information about, hey, pilots, you're stalling, they do the opposite. So what's going on? The public outcry from the Colgan air crash in New York was so loud and persistent that it eventually pushed Congress to pass a new law called the Airline Safety and Federal Aviation Administration Extension Act. And what it forced the industry to do is to take another hard look at stall, although we've been staring at this problem for over 100 years. But yet, we took another deep dive into it, and what we concluded is that there's nothing necessarily per se wrong with angle of attack sensors, nothing wrong with notifying the pilot about the stalls in the cockpit. But where the gap is that we had a gap between the systems and the human side of the pilots. We had adopted this stall prevention strategy, and on paper it looks like it should work. We're telling the pilot what to do, they just need to follow the instructions. And in the calm structure and serenity of the classroom, or maybe their check ride, all this works out. It totally makes sense. All of us would in here would look at this and say, yep, that makes sense. Pilots just need to follow what they're doing. Unfortunately, that scenario is idealistic and doesn't represent the messiness of life. All those stories I told you is that the pilots had another problem to work on. They had icing, they had a computer problem. Anything that comes up or goes wrong in the airplane is the responsibility of the pilot. It could be an engine fire, it could be weather, it could be a system malfunction. It all lands on the pilot to figure it out and to solve it. And as they're working whatever problem it is, understandably, their stress level goes up. And then they get surprised by the stall, the lights and the horns and the shaking, and that expands the level of stress in the cockpit. Psychologists tell us that in times of stress or anxiety, or when we feel that our lives are threatened, we tend to go to our default responses, what we're most comfortable with. And I've sketched this out, what I think this looks like in the cockpit. So we start out with a threat. It's a stall. And then, perfectly reasonable, we want to notify the pilot, hey, you have a stall. You need to deal with this. But the pilots are already stressed because they got another problem they're dealing with. And what we've done is we spiked that stress now and triggered their self-preservation, and their default response is they see their altitude and they want to pull. So the angle of attack sensor, although on paper it makes sense, on engineering it makes sense, we notify the pilots what to do. But what we didn't realize is that that act was triggering the opposite behavior in the human of what we wanted. So as they pulled, they made the stall worse, which made the alerts louder, which raised their stress, which caused them to pull even more, and they would spiral in. So how do we fix that? Well, a key piece of that law was the introduction of what's called Upset Prevention Recovery Training, UPRT. And it changes the way we train pilots about stall. And in the safety of a flight simulator, we do our best to recreate the messiness of life. So we have pilots flying, and we don't tell them. We surprise them with an engine fire or a computer problem or icing. And as the pilots in the simulator are working that problem, we then surprise them again by pushing the stall button. And then the lights go off, the horn goes off, the sirens and the shaking said, hey, pilots, you're stalling. And we teach them that whatever it is that you have going on in here, if you hear that stall warning system go off, you shove that column forward. And we do it to them over and over and over and over again, rewiring the brain so that in the context of a stall, their default response is to shove that column forward, executing the recovery. So, thank you for hanging with me. I know that's heavy. Not quite done with the angle of attack sensor, though. There was another system that we developed hoping to, once and for all, solve the stall problem. It was called a Maneuvering Characteristics Augmentation System, or MCAS. First introduced in 2017 on a brand new airplane called the Boeing 737 MAX. How this system worked is that the MCAS had an angle of attack sensor, and just like before, if it sensed that the angle of attack was getting too high and stalling, it would send a signal out. But unlike before, instead of sending the signal to the pilots, it said, no, pilots, you're going to screw this up. I'm going to send it the other way, and it sends it to the tail. And it moves the stabilizer to push the nose down automatically. Doesn't even tell the pilots that this is happening. Pilots are too busy working on another problem. We're going to take care of this messy stall for them, just automatic. We're just going to take care of it. And so the MCAS system will shove the nose down automatically, preventing the stall. Does this look familiar? Yeah, full circle, 100 years later. This is the idea that Orville Wright came up with. So, how did we do? Well, those of you know, many of you know that we've had some incidences with this system on the Boeing 737 MAX. The first was the Lion Air Flight 610 in October of 2018. And then just 5 months later, the Ethiopian Airlines Flight 302 in March of 2019. Both of them were Boeing 737 MAXs. Both of them had MCAS. Both flights were very, very, very similar. They took off, had a normal takeoff, and were climbing out, gaining altitude. And then at some point, the angle of attack sensor on the MCAS sensed, uh-oh, the pilots have stalled. They've gotten their nose up too high. And on both flights, the MCAS takes over, says, no worries, I'm going to take care of this, and started shoving the nose down on both of these flights, trying to save them from stall. Both pilots on both flights, by this time, presumably had their new UPRT training, looked down, saw their altitude, grabbed the column, and pulled. Pulled and pulled and pulled, fighting the MCAS, trying to save their lives from the stall. Unfortunately, neither flight survived. So what happened is that both these flights were very, very similar. The angle of attack on both flights, the angle of attack sensor on both flights sensed that the airplanes were stalling and sent the signal out to the tail. MCAS responded and started shoving the nose down. The problem is that on both flights, the airplanes were fine. They didn't stall. Pilots were doing great. What had happened, though, is that on both flights, the angle of attack sensors were broken. They were miscalibrated. They were telling the MCAS there was a stall when there was not a stall. And for reasons that only Boeing should answer to, they designed the MCAS so that the angle of attack was a single point of failure. In other words, the MCAS would automatically follow the bad data without verifying its accuracy against another source, driving the nose down deeper and deeper into a nosedive. And the pilots were right. They were responding to the nosedive. They had no idea what was going on, and they were trying to save the airplane from the MCAS. So this unfortunate design decision by Boeing not only resulted in 338 deaths, but their brand new airplane, they had to ground it for 2 years as they fixed the problems. And we estimate that Boeing has lost upwards of $100 billion solving this with the redesign and legal fees and liability and lost sales. So there you are, the angle of attack sensor. So next time you take an airline flight, think about the angle of attack sensor out there and why it's there and what it's doing. And thank you.